We're continuing our discussion of how spinors are used in particle physics. In the previous video, we discussed the theory behind the Dirac equation, including what the gammas mean, what Dirac spinors are, and the concepts of left and right chirality. In the next few videos, I'm going to be working up to the solutions of the Dirac equation. To help us understand the solutions of the Dirac equation better, in this video I'm going to solve the Klein-Gordon equation. Then in the next video I'll solve the Proca equation. The Klein-Gordon equation describes a scalar field and has wave-like solutions. The Proca equation describes a vector field, and it also has wave-like solutions. But the vector nature of the field allows waves with the same frequencies to have different polarizations, like horizontal, vertical, and longitudinal polarizations. Finally, the Dirac equation describes spinor fields, and also has wave-like solutions. But the spinor nature of the field allows waves with the same frequencies to have either spin-up or spin-down orientations. We'll also see that the Dirac equation has both matter and antimatter solutions, and this is related to the concepts of left and right chirality. We'll also talk about how chirality relates to the helicity of a spinor particle. Each of these three equations will get its own video explaining the solutions. We'll start in this video with the Klein-Gordon equation solutions for scalar fields. Now, all of the fields in this video are going to be purely classical fields, which means we can know the exact field values and field momenta together at the same time, so the fields are not yet quantized. If you want to see how to use commutators and anti-commutators to quantize these classical fields to get quantum fields, you can watch video 21 in this series. So let's start with the Klein-Gordon equation, which describes the behavior of a relativistic scalar field phi. As a review of video 21, a one-dimensional scalar field is like a one-dimensional collection of masses on springs, all connected with rubber bands. X gives the location of a mass along the x-axis, and phi of x gives the amplitude of the mass located at position x. The kinetic energy of a specific mass is related to the square of the time derivative of phi of x, which indicates how fast the mass is shaking. Since we'll be working with special relativity, we always put a factor of the speed of light c next to the time t to give units of meters, which puts time on equal footing with space coordinates. The potential energy for a mass due to the extension of its spring is related to the square of the amplitude phi, so how much the spring is extended, as well as the stiffness of the spring, which is denoted with a spring constant. In field theory, we commonly write this spring constant as mass times the speed of light c divided by the reduced Planck's constant h bar. So this is a mass term, and we can think of the field's mass as sort of like the field's stiffness, or how difficult it is to excite the field. The factors of c and h bar also help give this term consistent units with all the other terms in the equation, which have units of 1 over distance squared. With purely classical fields, the factor of h bar is often left out, but I'm going to leave it in for these videos, even if we are dealing with classical fields that have not been quantized yet. Finally, there is also potential energy due to the rubber bands connecting the masses. When two neighboring masses are at different amplitudes, the rubber bands will try and pull them back together. So this potential energy is related to the square of the derivative of phi with respect to x. We say that these energies are really energy densities, because they give us the energy per mass located at position x. Taking the kinetic and potential energy densities, we can use their sum to get the field's Hamiltonian density, and use their difference to get the field's Lagrangian density. To get the equations of motion for the field, we can put this Klein-Gordon Lagrangian through the Euler-Lagrange equation for fields. To do this, I'm going to rewrite the derivatives using subscript notation. Now, with the field Euler-Lagrange equations, we treat the field phi and its derivatives as independent variables. So taking the partial derivative with respect to phi, all terms go to 0 except the last one, where power rule decreases the power by 1 and brings a factor of 2 in front. For taking the derivative with respect to partial CT phi, all terms go to 0 except the first one, and power rule gives us partial CT phi as a result. Similarly, for the partial x phi derivative, we get negative partial x phi as a result. Knowing all this, if we expand the sum in the Euler-Lagrange equation to include the time and x indices and plug in the derivative terms, when we bring everything to one side, we get the Klein-Gordon equation. This is the equation of motion for a scalar field phi that we described with the Klein-Gordon Lagrangian. If we want to extend this to a three-dimensional Klein-Gordon field that depends on x, y, and z, we just need to include gradient terms in the potential energy density for the y and z directions. And these get corresponding terms in the Klein-Gordon equation. Now, if we pull out the phi field in front, we can notice all these second derivative terms in the four space-time directions. The time derivative has a plus sign in front, and the space derivatives all get minus signs. We can write this sum of four terms using arrays with an inner row-column product, if we include this matrix in the middle that have the correct signs along the diagonal. This is the Minkowski metric eta that you should recognize from special relativity. We can also write this array multiplication using Einstein's summation notation, where we have implied summations over the mu and nu indices that range from 0 to 3. Here, index 0 indicates the time ct, and indices 1, 2, 3 indicate the space directions x, y, z. With these space-time summation indices, it's very common to use the notation of raising and lowering indices using the Minkowski metric eta. For example, we can take the eta summed with a derivative with a lowered index and replace it with a derivative with a raised index. This allows us to write the Klein-Gordon equation like this. So now that we have some background with the Klein-Gordon equation, let's actually solve it. This is the Klein-Gordon equation with 3 dimensions of space and 1 dimension of time, also called 3+1 space-time, and its solution is a little more complicated. So to simplify things, we'll get rid of the y and z directions and just look at the Klein-Gordon equation with 1 dimension of space and 1 dimension of time, which is the 1+1 space-time version. So we're only going to look at the time and x terms, and ignore the y and z terms. The solutions to this Klein-Gordon equation are given by cosine waves, where omega is the wave's angular frequency in time, and k is the wave's angular frequency in space, also called the angular wave number. You might find it a bit weird how I'm dividing the frequency by c and then multiplying time by c, since these factors would just cancel out. But these extra factors of c ensure both time and space have units of meters, and ensure that frequency and wave number both have units of 1/meters. If you like, you can cancel these c's or use natural units and set c equal to 1, but I'm going to leave these factors of c in. To see why this cosine solution works, let's look at the Klein-Gordon equation term by term. To take the derivative with respect to ct, we treat ct as a single variable in the formula. Equivalently, we can treat this as 1/c times a time derivative if you want. So the derivative of cosine is negative sine, and by chain rule, we get a factor of omega over c. If we take the derivative again, sine becomes cosine, and we get another factor of omega over c by chain rule. So for our cosine solution, we see that phi and the second derivative of phi with respect to time are proportional, where the proportionality constant is the negative frequency squared. If we look at the x derivative term, we see that we get something similar, except the proportionality constant is the negative wave number squared instead. So looking at the Klein-Gordon equation and assuming our cosine solution, we can replace the second time derivative with negative frequency squared and replace the second x derivative with negative wave number squared. Finally, we can also combine these terms together and divide both sides by the field phi. In the end, we get this relationship here between mass, frequency, and wave number. This is called the dispersion relation, and I'll explain why in a moment. So to solve the Klein-Gordon equation, we can pick any cosine wave with any frequency or wave number, as long as they obey this dispersion relation. It's also worth noting that if we take this basic cosine solution and include a scale factor a and a phase factor theta, this is still a solution to the Klein-Gordon equation, because the scale and phase factors don't impact the differential equation. You might also recall the cosine angle sum identity. This allows us to split the cosine into a sum of a term with cosines and a term with sines. And we can rewrite the scale factor a times the trig functions of theta as new scaling constants. So giving the cosine wave a phase factor is the same thing as writing a sum of a cosine wave and a sine wave. Another way to rewrite the basic cosine solution is using Euler's formula. Taking the real part of a complex exponential is the same thing as a cosine wave. We can also include the complex exponential of the phase factor theta into the real scale factor a to give us a new complex scale factor. So we can use the real part of this solution for real fields, or we can use the entire complex wave if the field is complex. Now, one last thing to note about the Klein-Gordon equation is that it's linear. This means that if we have a wave phi1 and another wave phi2, which both solve the Klein-Gordon equation, then their sum, phi1 plus phi2, is also a solution to the Klein-Gordon equation. This is easily checked as seen here. This means that we can add an infinite number of different wave solutions together to get another solution. We can even do an infinite continuous sum over basic cosine solutions by doing an integral over the wave number k, since k is a continuous variable. It's also worth noting that, in the most general case, both cosine and sine waves solve the equation, and we can alternatively write the solutions using complex exponentials if we want. So we know for the 1D Klein-Gordon equation, the basis solutions are sinusoidal waves that obey this dispersion relation. And since the Klein-Gordon equation is linear, we can add any number of these basic sinusoidal solutions together to get a new solution. Generalizing to the 3 space-dimensional version of the Klein-Gordon equation is easy. We just use the same basic cosine solution, but using x, y, and z terms, where each of x, y, and z has its own wave number. If we define omega over c as the time component of the wave number, these 4 k components can be assembled into a 4-vector called the wave number 4-vector. And we can rewrite the cosine argument as a simple summation. We call these basic solutions plane wave solutions, because the components of the wave number vector indicate the orientation of planes in the wave. Now, since the Klein-Gordon equation has wave-like solutions, it's worth asking what speed these waves travel at. One basic way to find the wave speed is to take the ratio of the angular frequency omega and the angular wave number k. This ratio has the expected units of velocity. But we can also visualize the wave speed on a space-time diagram. Frequency indicates how many wave peaks we see in a given unit of time at a constant position, and wave number indicates how many wave peaks we see in a given unit of space at a constant time. If we know what these densities are, we can draw the world lines of the peaks of the wave on the space-time diagram, and the slopes of these wave peak world lines will tell us how fast the wave is traveling. So let's compute this ratio omega over k for our Klein-Gordon solutions. To do this, let's start with our dispersion relation for the Klein-Gordon equation. So we'll bring the wave number term to the other side, changing its sign. Then we'll divide both sides by k squared, and then multiply both sides by c squared. Now, to get our desired ratio omega over k, we just take the square root of both sides, and we get this for the wave velocity. Now, this result is actually a bit concerning. If we were dealing with a massless field where m equals 0, then the wave speed would be the speed of light c, which is fine. But if the field has a non-zero mass, then the speed of the wave is actually greater than the speed of light c, since this term under the square root sign is always greater than 1. So you might think this means we've broken the rules of special relativity. However, it turns out this result is actually fine if we understand the difference between the phase velocity of a wave and the group velocity of a wave. As you can see here, this traveling wave has an outer envelope, which is traveling more slowly, and inner wave peaks that are traveling more quickly. The slower outer envelope is what is actually capable of transmitting information. So if we want to obey the laws of special relativity and not send information faster than light, this envelope's group velocity must be less than or equal to the speed of light c. The fast inner wave peaks are not capable of transmitting information. So it's actually fine if the phase velocity of these peaks is faster than light. The omega over k ratio we calculated before is the phase velocity. So it's fine that this is faster than light, because this will not transmit information. If you think about it, a single traveling cosine wave that looks the same everywhere in time and space cannot be used to transmit any information. Now, what about the group velocity? Well, let's consider a Klein-Gordon solution that is made of a sum of two basic cosine waves, with frequencies and wave numbers labeled 1 and 2. Now, if we take the cosine angle sum trig identity and the cosine angle difference trig identity and add them together, we see that a sum of two cosine waves can actually be rewritten as the product of two cosine waves. We can also switch some of the variables around to get this easier to understand formula here. So if we have our two Klein-Gordon waves summed together here, we can use this new trig identity to rewrite it as a product of two cosine waves. One where the frequencies and wave numbers are added, and one where the frequencies and wave numbers are subtracted. The cosine with the addition signs represents the inner waves that travel with the wave's phase velocity. And the cosine with the minus signs represents the outer wave envelope that travels with the wave's group velocity. So the group velocity would just be the omega over k ratio for this outer cosine wave, which is omega 1 minus omega 2 over k1 minus k2. We can also write this as delta omega over delta k. Now here we had a sum of just two cosine waves, but if instead we had a continuous spectrum of different cosine waves with different frequencies and wave numbers, this difference formula for the group velocity would become a derivative. So this derivative is what gives us the equation for the group velocity of the wave envelope. Let's return to our Klein-Gordon dispersion relation from before. If we isolate omega squared and then take the square root, we can then take the derivative of both sides with respect to k to calculate the group velocity. Treating the square root as a 1/2 exponent, we can use power rule to decrease the exponent by 1 and put a factor of 1/2 in front, and then use chain rule to get an extra factor of the derivative of k squared, which is 2k. The 1/2 and 2 cancel, and the negative 1/2 exponent gives us a square root in the denominator. So this is the group velocity formula. For a massless field with m equals 0, the group velocity simply becomes c. But for a massive field, this term in the denominator is always going to be bigger than k, since m is positive, which means that the group velocity is always going to be less than the speed of light. So this shows us that the speed of information contained in the wave cannot exceed the speed of light. So the Klein-Gordon field obeys the laws of special relativity. Now I'll finally talk about why this relation is called the dispersion relation. If we imagine a set of basic cosine solutions with different frequencies and wave numbers, then each basic wave will travel at a different phase velocity depending on the value of its wave number k, since the mass m is constant for the whole field. We can see that when k is very large, the phase velocity will be about the speed of light. But when k gets smaller and smaller, the phase velocity will get bigger and bigger. So this means that our collection of basic cosine waves will all travel at different speeds. So any envelope shape that they have when the wave starts traveling will gradually start to deform or disperse as the wave travels along. And this is why we call this the dispersion relation. However, in the special case of massless fields where m equals 0, the phase velocity for every basic cosine wave is always the speed of light c, regardless of what the wave number is. This means that the wave envelope in massless fields will not disperse and will maintain its shape forever. Now, there's one last thing I want to talk about, which is the complex version of the Klein-Gordon field, and how it relates to antimatter. So we've already seen the real version of the Klein-Gordon Lagrangian, where the function phi outputs a real number. And when we put this through the Euler-Lagrange equation, we get the Klein-Gordon equation. But now let's consider the complex Klein-Gordon Lagrangian, where phi outputs a complex number. In this Lagrangian, instead of squaring the terms, we take the squared magnitude of the terms. This means each term in the sum involves an expression times its complex conjugate. For the derivative terms, since the variables we are taking derivatives with respect to are real, they are not affected by the complex conjugate. So the star can just be moved to phi. Now, it's worth noting that one complex field can be viewed as two real fields, since the complex phi has both a real part and an imaginary part. However, when dealing with the field equations, it's more useful to consider phi and its complex conjugate phi star as the main field variables instead. So with this complex Lagrangian, if we put it through the Euler-Lagrange equation, varying with respect to phi, we get the Klein-Gordon equation for phi star. But we can also put this Lagrangian through the Euler-Lagrange equation, varying for phi star, and we get the Klein-Gordon equation for phi. So we actually get two Klein-Gordon equations here. Also, these overall factors of 1/2 don't impact the physics, so we typically remove them from the Lagrangian. So here, phi represents matter particles, and phi star represents the corresponding antimatter particles, with opposite charge. So scalar matter and antimatter particles can sort of be viewed as different types of excitations in the same scalar complex field, related by the complex conjugate. So if the standard matter excitation is a complex exponential with a positive sign, then the corresponding antimatter excitation is a complex exponential with a negative sign. These two excitations have the same real part, but opposite signed imaginary parts. Now, to understand electric charge, we'll look at this Lagrangian's U1 symmetry, where U1 is the group of all 1x1 unitary matrices, which is just the set of complex numbers with magnitude 1. If we transform phi by multiplying it by a complex phase, then phi star will transform with the same complex phase but in the opposite direction, since the complex conjugate will change the sign of the I in the exponent. If we take our Lagrangian and apply this U1 phase transformation to the field phi, all of these complex phases do not depend on the spacetime variables, so we can pull them in and out of the spacetime derivatives. This means that every positive phase will get cancelled by a corresponding negative phase, so the overall Lagrangian is left unchanged by this U1 phase transformation. Now, a theorem called Noether's theorem tells us that every continuous symmetry in a Lagrangian will always result in a conserved quantity. We can see this conserved quantity if we look at the Klein-Gordon equations for phi and phi star. We'll multiply the phi equation on the left by phi star, and multiply the phi star equation on the left by phi. Now let's subtract the equations, which will cancel the mass terms but leave the derivative terms. Now I'll add and subtract this term with derivatives of phi and phi star. These first two terms have a lower mu derivative on the left on the first term and on the right in the second term, so they can be grouped together using product rule in reverse. The same is true for grouping the third and fourth terms. Overall, we get this equation here equaling 0. We can consider this formula here in the brackets to be a current for vector J, and this obeys a continuity equation. This basically means there's a charge density, which is the time component of J, and the only way this charge density can change over time is if there's a convergence or divergence of some current at a given point. This is the electric charge current, and since it obeys the continuity equation, this means that total electric charge is conserved over time. Now, I will point out that this 4-vector current we've defined here is purely imaginary. We can see this by taking the complex conjugate of the formula, then distributing the star to all the terms inside, and seeing that we get the negative of the original 4-vector. Since the complex conjugate equals the negative, this means that J is purely imaginary. Because of this, we usually define J by multiplying this formula by the complex I to make the result purely real. Now, everything we've said so far is true in classical field theory, but let's jump ahead and take a quick look at quantum field theory, where the field functions become quantum operators. This will lead us to creation and annihilation operators for both matter and antimatter particles. There are also number operators for counting the number of matter and antimatter particles, with a given wave number k. There is also an electric charge operator Q, which is related to the difference in the number of matter and antimatter particles, and this is conserved over time. The Higgs field, related to the famous Higgs boson, is actually a pair of complex scalar fields in its original form, and its free behavior, ignoring interactions, is described by the complex Klein-Gordon field. So let's sum up everything we've learned about the Klein-Gordon equation in this video. We learned that the Klein-Gordon Lagrangian is inspired by an infinite field of masses on springs connected with rubber bands, and each term in the Klein-Gordon Lagrangian represents either kinetic energy or potential energy in this field. When we put this Lagrangian through the Euler-Lagrange equations, we get the Klein-Gordon equation, which describes how the field phi evolves over time. This is the 1 + 1 spacetime version of the Klein-Gordon equation, but we can also write down the 3 + 1 spacetime version with x, y, z variables. The basic solutions to the Klein-Gordon equation are sinusoidal waves, which can be written in many different ways. And since the Klein-Gordon equation is linear, any sum of scaled sinusoid solutions will give another valid solution. We also learned about the difference between the phase velocity and group velocity of Klein-Gordon solutions. It is only the group velocity that is capable of transmitting information, so it is limited by the speed of light. However, the phase velocity does not have this limit. Finally, we learned about the complex Klein-Gordon field, which gives both matter and antimatter solutions. And we learned that the U1 symmetry of this Lagrangian leads to a conserved current, which is the electric current 4-vector, and this obeys a continuity equation. In the next video, we're going to look at the Proca Lagrangian, which describes vector fields.